Historical insights from the world of human measurement in space physics. Historical insights from the world of measurements and physics laws with particular significance for the exploration of spaceships designs, the laws of thermodynamics, 1824. Maxwell electromagnetic equations, 1865. The periodic table, 1869. The Michelson-Morley experiment, 1887. The Rydberg formula, 1888. Historical insights from the world of measurements and physics laws with particular significance for the exploration of spaceships designs, the Planck-Eta model, 1900. The Einstein era, 1917. Pauli, the exclusion principle, 1925. The Schrödinger equation, 1926. The Heisenberg uncertainty principle, 1927. The Hubble constant, 1929. The Dirac, 1933. The Fermi era, 1942. The Casimir effect, 1940. Shannon, information theory, 1940. The Feynman era, 1970. The Hawking radiation, 1974. The Alcubierre drive, metric, 1994. The framework operations of the constants in physics. Perspectives on topologies and technologies for the exploration of space. Perpetual design directions for the significant role of dimensions on structures in physics for space exploration. Important notice: this portion of presentation contains intentionally simplified information for nuclear physics without prior notice for numerical values results. Tangible experimentation outside from a nuclear federal lab facility supervision or from a supervised university is strictly prohibited. This education material is covered under the jurisdictions and the laws of the USA. Radioactive decay is the process in which an unstable nucleus spontaneously loses energy, by emitting ionizing particles and radiation. The three principal modes of decay are called the alpha, beta and gamma decays. Radioactive decay is statistical in nature, and we can only describe the evolution of the expectation values of quantities of interest, for example the number of atoms, that decay per unit time. If we call the number of radioactive nuclei n, the number of decaying atoms per unit time t, is dn dt, it is found that this rate is constant in time and it is proportional to the number of nuclei themselves. Dn to dt is equal to lambda nt, where dn to dt is also called activity. The constant of proportionality is called the decay constant. We can also rewrite the above equation as lambda is equal minus dn divided to dt to n. The fact that this probability is a constant is a characteristic of all radioactive decay. Momentum: the momentum is also shared between the electron and the neutrino. Thus the observed electron momentum ranges from 0 to a maximum possible momentum transfer. Angular momentum: both the electron and the neutrino have spin half-one parity. It turns out that parity is not conserved in this decay. This hints to the fact that the interaction responsible violates parity conservation. Charge: thus the creation of a proton is for example always accompanied by the creation of an electron. Leptons number: leptons are fundamental particles including the electron, muon and tau, as well as the three types of neutrinos associated with these three. The lepton number is +1 for these particles and -1 for their antiparticles. Then an electron is always accompanied by the creation of an antineutrino, for example, to conserve the lepton number initially 0. This refers to the beta decay that is a demanded process, while we need to know details for the nucleus structure. Remember, nuclei does not changed in decay, it is just change energy level to a lower one. Beta emission has direction opposite the nuclear spin in violation of the conservation of parity. When we lowering the temperature pre-configuration procedure in a penning trap case, we are able to polarize the nuclear spins along the direction of an applied magnetic field. So, we can measure the direction of the emitted electrons, that are much more caused of the non-conservation parity. The idea that nature at a very fundamental level can tell the difference between left-handed and right-handed systems is a radical one. The behavior of physical particles, charge conjugation C, parity P and time reversal combine to constitute a fundamental symmetry called CPT invariance. In simple classical terms, time reversal just means replacing T by T, inverting the direction of the flow of time. Reversing time also reverses the time derivatives of spatial quantities, so it reverses momentum and angular momentum. Newton's second law is quadratic in time and is invariant under time reversal. Its invariance under time reversal holds for either gravitational or electromagnetic forces. ESD. Hypothesis for further research investigations platforms. In general, the term relativity is completely different when we deal with nuclear physics. However, phenomena of classical relativity implications can emerge as time dilation and length contraction can affect propulsion and navigation structures in a moving reference platform with a quarter of the speed of light. The CPT invariance initially is a proper research study framework, placing research augmentation platforms configurations for exotic materials in various structures combinations that can be tested to increment safety stages on issues between internal fracture or tolerances of the materials and structure detachment for outer-only active energetic spacecraft surfaces, something that is very helpful for the critical overall structural conditions monitoring. Instrumentation of the CPT invariance in a monitoring plot is a critical component for a space engineering control deck, because for spaceship systems engineering terms provides basic configurations for navigation and propulsion. CPT invariance itself has implications, which are at the heart of our understanding of nature, and which do not easily arise from other types of considerations. Integer spin particles obey Bose-Einstein statistics and half-integer spin particles obey Fermi-Dirac statistics. Operators with integer spins must be quantized using commutation relations, while anti-commutation relations must be used for operators with half-integer spin. Particles and antiparticles have identical masses and lifetimes. This arises from CPT invariance of physical theories. All the internal quantum numbers of antiparticles are opposite to those of the particles. A penning trap is a combination of a homogeneous magnetic field and an electrostatic quadrupole potential. This kind of trap is particularly well suited to precision measurements of properties of ions and stable subatomic particles. Penn trap is very useful to store qubits and antiprotons. So, penning trap as a technique, it is a useful initial apparatus for design and test structures for issues on navigation and propulsion that are using concepts from the world of deep physics. Also, some properties of johnnium are indeed very different from a typical atom. The charge undergoes cyclotron motion around the trap axis, and oscillates along the axis. An inhomogeneous magnetic bottle field is applied to measure the quantum properties by the continuous Stern-Gerlach technique. Energy levels and G-factor of the particle can be measured with very high precision. Johnnium studies of electrons and positrons are one of the best tests of QED, and yield precise determinations of the fine structure constant. Your basics in brief. Parity in beta decay is not conserved. Nuclide is not changed in gamma decay, it is just change energy level to a lower one. Reversing time also reverses the time derivatives of spatial quantities, so it reverses momentum and angular momentum. Newton's second law is quadratic in time and is invariant under time reversal. Instrumentation of the CPT invariance in a monitoring plot is a critical component for a space engineering control deck, because for spaceship systems engineering terms provides basic configurations for navigation and propulsion. Penn trap is very useful to store qubits and antiprotons. Integer spin particles obey Bose-Einstein statistics and half-integer spin particles obey Fermi-Dirac statistics. Johnnium studies of electrons and positrons are one of the best tests of QED, and yield precise determinations of the fine structure constant.